stable eigenvalue of the vector. Okay? Just understand that with the similarity transformation matrix T, alright? You can use either a state X or state X bar, where X is T X bar. That will result in the state matrix. State matrix is A. Okay? The state matrix of A bar is now T inverse of AT. Alright? Just understand that the state matrix A bar will have the same eigenvalues as the state matrix A. Okay? So A bar is the state matrix for states X bar. A is the state matrix for states X. Okay? The eigenvalues of A bar are the same as the eigenvalues of T. Alright? Provided that T is full row rank, it's non-singular. Okay? So how does this relate to this? So we are telling you that there are actually two formats that you can write a state space equation. One is called a controller canonical form, and the other is called observer canonical form. Okay, just imagine that the controller canonical form has the state matrix A, and the observer canonical form has the state matrix A bar, whereby they are just related through a similarity transformation. Okay, so essentially they share the same closed-loop transfer function, they share the same eigenvalues, because they share the same closed-loop poles. Alright? But why do we need two different forms? Okay? We need a controller canonical form because it's more convenient for us to design a controller. We need the observer canonical form because it's more convenient to design an observer. Okay, which we'll elaborate in further details. Alright, just understand that we need this form, the controller canonical form, because it will be easier for us to design a controller plane. Okay, we need an observer canonical form because it's easier for us to design an observer L. Alright, but they are related through a similarity transformation. So they have the same eigenvalues, they have the same closed-loop transfer function, they have the same closed-loop poles. Alright? Okay, so let's move on. Controller canonical form. Alright, we say that we can write a state space model ABCD in this way. So, you see that A can be written as minus A1 minus A2 all the way to minus A, and it's quite meaningless unless you know that transfer function is as this. Okay? So this is for transfer function B1 s power n minus 1 plus dollar dot Bn minus 1s plus Bn over s power n plus A1 s power n minus 1 plus dollar dot plus A power An minus 1s plus Bn. Okay? If you have this transfer function, you can write the controller canonical form in this way. Okay, so you can observe that for the first row, we have coefficients, minus A1, minus A2, all the way to minus An. And then the bottom is just a triangular matrix. So bottom is 1, 0, 0, 0, 1, 0, 0, 0, 1, all the way 0, and all the way to 0, 0, while the 0, 1, 0. So in between is all zeros. Okay, it's all 1. It's a triangular matrix. Okay, B is standard, it's always 1, and all the way. C is the coefficient of the numerator, so it's B1, B2, all the way to Bn, and D is always 0. Okay, an example is if you have a 2 by 2 matrix, a second order system, A will be minus A1 minus A2, 1, 0. Okay, and B will be 1, 0, and C will be B1, B2. 3 by 3, A is minus A1 minus A2 minus A3, and then 1, 0, 0, 0, 1, 0. B is 1, 0, 0, C is B1, B2. Okay, so in the exam, you may be given a transfer function and asked to write what is ABC was this space model. Okay, And this particular format has a name, which is called the controller canonical form. Alright, and we say that any completely controllable system can be expressed in this form. Alright? Before you do that, you need to introduce some idea of controllability. So for last year, there was a question on define controllability. Okay, so you have read that in words. What is controllability? Okay, so there are two terms that we use in control systems: controllability and stabilizability. Alright, so what we want to do is we want to understand whether we can steer the state via a control input to certain locations in this space. You don't have to memorize this. What you should memorize is this. Okay? So controllability is whether a given initial state of the system x0 can be steered to the origin in finite time using an input ut. Okay, why origin? Because there's no reference in it. Okay? Our system is x dot equals to ax plus bu. Input is u and output is x. A vector. Okay? So there's no reference. So we say that a system is controllable if we can steer the state x back to origin. Okay, meaning the dynamics is A. It's very stable. Alright, in a finite time, you see an input u. Okay? If you want to get full marks for the definition of controllability of this, the state x0 is said to be controllable if there exists a finite time interval 0 to t and certain input u for the t interval subset of 0 to t such that xt, meaning x, the state at the end of the time interval t, is 0. Okay, it's an origin. If all the states in x, x1, x2, x3 are all controllable, then the system is said to be completely controllable. Okay? Alright, another definition that's related to controllability is reachability. Alright, what's the difference between controllability and reachability? So we say that if you have a state x bar, which is initially not at 0. Okay, we say that it's reachable from the origin if given an initial condition. There exists a certain finite time interval from 0 to t and a certain input u for t subset from 0 to t, such that at the end of the day, the state at time t is x bar. Okay? So you can reach a certain location x bar at the end of the finite time interval. So the state x at time interval time t is x bar. And if all states are reachable, x1, x2, x3 are all reachable, the system is said to be completely reachable. Alright, final remark. Okay, there's usually no distinction between complete controllability and complete reachability. Okay, by discrete time, there's a small difference. So in discrete time, we talk about updating the states. The next state based on the current state. Alright? So if we have this x k plus 1, so x k plus 1 is the next state, which is 0. You understand that this system is obviously completely controllable because the next state immediately goes to the origin, right? Because x k plus 1, whatever this state is over 0, immediately goes to origin. Okay? But can you reach any other non-zero state? No, because the next state is always 0. Okay? So it's completely controllable by other non-zero states are not reachable. Alright, and it's just a remark to say that we use controllability to cover this problem too. Okay, the next thing that is more important is how do you test whether a system is controllable? Okay, so there's a start here. One thing that we know. So you have a state space model, x star equals x plus bu, y is cs plus du. We define your controlability matrix. Okay, gamma c, bracket a comma b, as b for the first column, ab for the second column, a squared b for the third column, and all the way to the last column, a to the power 10 minus 1b. We say that this model is completely controllable if and only if gamma CAB has full row rank. A meaning is non-singular. Okay, the rows are linearly independent. Okay, example. So if this is a completely controllable state space model, alright, if you have A, which is minus 1, 1, 2, 0, B, 1, minus 1. Your controllability matrix is, the first column is B, so 1 minus 1, so rather 1 minus 1. The next column is AB. So you compute AB, A is this, B is this. How do you compute? Minus 1 times 1, minus 1, plus 1 times minus 1. So minus 1 plus minus 1, minus 2. Okay? 2 times 1, 2, plus 0 times minus 1, 2. Okay, so AB is minus 2, 2. Alright, BAB is 1 minus 1, and then minus 2, 2. Okay? You can see that the first row is the second row times minus 1. Yeah? So these two rows are dependent. Okay, they are not linearly independent, they are dependent. So the rank gamma CAB is 1, which is less than 2. Okay, thus the system is not completely controllable. Okay? Another example. A is minus 3, 1, minus 2, 0. B is 1, minus 1. B, 1 minus 1 is just right down here. AB. Minus 3 times 1 is minus 3. Plus 1 times minus 1 is minus 1. So minus 3 minus 1, 2 minus 4. Minus 2 times 1 is minus 2. Plus 0 times minus 1, 0. So minus 2. Okay, so minus 4 minus 2. The first row is 1 minus 4. The second row is minus 1 minus 2. They are independent. Okay, so clearly the rank is 2. Thus the system is completely controllable. Alright. So in the exam you can expect that first question is the system controllable. So you do this test. Okay. Just in case some of you still don't quite understand what we're going to say here. Just in case. If A is this, B is this. Alright, B is 1, 0. Compute AB minus 1, 1. So we have 1 minus 1, 0, 1. Okay? You can tell that the first row is different from the second row, right? Completely different. Completely independent. Alright, the rank is 2. Okay, so this non-singular. Full row rank. Okay? Alright. If you have the controllability matrix 1 minus 2 minus 1, 2, very obvious. It's not full row rank, it's singular. Okay? This is singular and its inverse does not exist. Alright? Remember below that. Singular matrix does not have an inverse. Okay? Because the row 1 as minus 1 is row 2. What about a third order controllability matrix 1, 0, 0, 2, 0, 0, and 0, 1, 1. Alright, you can check that the first row is the second row. Okay, second row is first row plus 2. Right? Okay, so overall, the rank of this is 2. Alright, so that is initial order 3. So it's not full row rank. Alright, so it's singular. Okay? What about 2, 0, 0, 0, 3, 0, 0, 0, 4? Alright? You can see that these 3 rows are totally different. Okay? So the rank is 3, it's full row rank, it's non-singular. Okay? And you can also tell that the eigenvectors for this is 1, 0, 0, 0, 1, 0, 0, 0, well, for the 3 columns. Okay? Do you feel better? Okay, so let's move on. Alright, if a system is not completely controllable, meaning some states are controllable, some states are not, we can break it down into a controllable and uncontrollable subsystem. Okay, so we call this a controllable composition. Alright, so if the system has a controllability matrix, rank A, that is less than the initial order of the system N, there exists a similarity transformation T, such that X bar is T inverse T. And this is exactly what you did know. Okay, and this A bar, you can break down into a controllable portion, A bar C. A non-controllable portion, A bar MC, or non-controllable. There's something in between, A bar 1, 2. Alright? So if you write it out in the space equation, so we have X bar dot, which is XC bar dot, and XNC bar dot, for controllable and non-controllable. This is equals to your A bar, which is AC bar, A1, 2 bar, 0, and A, AC bar. Okay? State. Alright? Where the controllable portion has dimension K, which is the rank of controllability matrix, and AC bar, B, C bar is completely controllable. Alright? Okay, so you can see that with this, you can break it down into a completely controllable portion and an uncontrollable portion. Okay, and you know that the controllable XC has the dynamics of XC bar dot defined by an input U. Okay, so you can control how XC bar will behave through an input U. Whereas for the uncontrollable XNC bar, there's no input, meaning you cannot control the states with any inputs. Okay? Alright? Okay, so say that caution must be exercised when you're trying to control a system with a non-controllable part. So as I said, the controllable part can be influenced by the input U or XC bar. The uncontrollable part cannot be influenced by any input. Okay, that's your X NC bar. But these two will add up together to form your output. Okay? The controllable subspace. Alright? The stability of the controllable subspace is determined by the eigenvalues of AC. The stability of the uncontrollable subspace is determined by the eigenvalues of A and C. Alright? So, the question is this system still stable? Alright? You can influence the eigenvalues of AC through an input. Alright? But you cannot influence the eigenvalues of A and C. But if the eigenvalues certain values of A and C are stable, meaning they are not unstable, they are stable. Okay, we say that the system is still stabilizable. Okay, because the uncontrollable portion is stable. Alright, in the past year exam question, there was what's the definition of controllability and what's the definition of stabilizability. Okay, so answer for the definition of stabilizability is this. It's stabilizable if the uncontrollable of states is stable. Okay? Alright. Alright, an example of something that is uncontrollable and non-stabilizable is constant disturbance model. Alright? Okay? So if you apply the definition of controllability, we say that controllability is if you have a initial condition which is non-zero, means here the state of the origin in a finite time interval. Okay? And stabilizable is if you have a non-controllable portion, this is still stable. Alright? So in this case, when x d dot is 0, this is a constant disturbance because there's no derivative. The derivative always 0 is a constant disturbance. So if a constant disturbance, alright? Okay, you can't stay equal to 0. Okay? For a constant disturbance, you can't stay equal to 0. Alright? On Moodle, there is actually a proof for why the controllable canonical form is like this. Okay, so let's say that this is totally optional. For those who are interested to know why a controllable canonical form looks like this, okay, it's available in Moodle. Alright? Okay, next. We move on to the definition of observability. Okay, so we say that there are two canonical formats. One is the controller canonical form, and the other is the observer canonical form. So obviously we go through a definition of controllability, we must go through a definition of observability. Alright? So controllability studies the possibility of steering the states to the origin in a finite time interval using input U. Observability studies the possibility of estimating the states from the output Y. Okay? Observability studies the possibility of estimating states X from the output Y. Why do you need to do that? Why is it important? Because some of the state variables are not accessible for direct measure. So if you are having a look, alright, you're interested in temperature, of course temperature is a measure. If you are interested in the concentration of oxygen, unless you have a super robust oxygen sensor, that will withstand high temperatures, maybe you cannot measure the concentration of oxygen. But you can measure the byproducts, the concentration of the byproducts from this chemical process that will allow you to estimate the concentration of oxygen in the plant. Okay, so you're making use of the output to estimate what are the states, and the state that you're interested in is the concentration of oxygen. Okay, so in this case, you cannot measure concentration of oxygen, which is the state that you like. Right? You can use the output to estimate this value. Alright, so that's why you want to understand observability. Okay, so it becomes necessary to estimate the unmeasurable state variables construct the control signal. Okay, as you say that it's state feedback control, U is minus Kx. So you need to know the state variable before you can design your control signal. So if you do not have information on the state variable, you find some method, okay, to estimate the states of it. Alright? Okay? So take for instance an example, if y, the output, y is cx plus du, e is 0 and c is 0, 1. X is inter dot inter. So what is y? Y is just inter. Right? So you say that in general, the dimension of the output y can be less than the dimension of the state x, because this x has two state variables. Y has only one value, which is one of the states. Okay? But if we can observe the output y over some time interval, then this can tell us something about the state. Alright? And this is what we call observability, the related issues in detectability. So in the exam, don't be surprised if they ask define observability and detectability. What the difference is, okay? Alright, so what's observability? Okay, answer is the definition here. Alright, so if you have a state, initial condition x naught, non-zero, we say that you can observe this. If x0 is x naught, then ut control signal is 0, or t bigger than 0. Then yt is 0, or t bigger than equals to 0. So it's unobservable if your output y is 0. T equals to t. Okay? It's unobservable if your output y is 0 and t equals to t. Alright, at the end of this finite time interval, the output y is 0. So you can observe anything. It's unobservable. Okay? At the end of the finite time interval, t, okay, at the end of the finite time interval, t, the output y is 0. The system is unobservable because output is 0. You cannot observe anything. You understand this? Right? Okay? But if you're asked about the definition, you don't need a perfect one. Okay? The system is said to be completely observable if there are no such non-zero initial state. It's unobservable. Okay? Alright? Reconstructability is whether you can reconstruct. So, reconstructability is what can be said about states x based on past values of the output. Alright, so can you reconstruct information about states based on past values of y? Alright? Okay? So if we look at an example to illustrate the difference between observability and reconstructability. Okay, so if we just look at this example first, x a plus 1 is 0, y equals to 0. So what you do is you substitute values. So with t, it's obviously okay. So when t is 0, you have x, t plus 1 is x1, which is 0, because this is always 0. T equals to 1 is still 0. Alright? So this system is clearly constructible for the t bigger equals to 1. Because we know for certain that xt is always 0. Okay? So based on past values, we know that it's always 0. You can reconstruct. But it's completely unobservable because it's always 0. Alright? Okay, versus this one, which is x k plus 1 equals to k, let's say. So you substitute k equals to 0, x1 equals to 0, substitute k equals to 1, x2 is 1, substitute k equals to 2, x3 is 2. Alright, this is reconstructible and it is also observable because there's some value. Alright? Okay? Reconstructible means can you reconstruct what is the state x based on how values of output y. Okay? Observability is as long as the output is not 0. Okay? And that can be used to tell you something about state. That's observable. Alright? Okay, so what is more important? Definition is definition. There's something to memorize, okay? And of course I hope you appreciate. But what is more important is the test for observability. Okay, so how do you test for observability? Same thing. You form an observability matrix. Okay? Gamma AC with these rows. So you have C, CA, all the way to CA power n minus 1. And we say that the system is completely observable if and only if this observability matrix has full column rank. Okay? Versus controllability test, we say that the system is completely controllable if the controllability matrix has full row rank. Okay? So in terms of observability, we're looking at full column rank. Okay, so how do you test observability? Actually, this is exactly the same as in the previous one. Okay, I write this because I want to highlight to you that controllability you check for full row rank and observability you check for full column rank. Alright? Shall we move on? Okay, alright. Okay. Okay, full row rank. Alright? Okay. So when you check observability, if ABC is given to you, you form the observability matrix CCA. So C is 1 minus 1. So 1 minus 1. CA, so CA is, you take the product of C and A. So 1 minus 1 is minus 3 minus 2 minus 0. So 1 times minus 3 plus minus 1 times 1. Minus 3 minus 1 is minus 4. 1 times minus 2 plus 0 times minus 1 is minus 2. So 1 minus 1 minus 4 minus 2. Check the columns. Okay? So the first column is 1 minus 4. The other column is minus 1 minus 2. So obviously there are two independent columns. Okay? So the rank is full and the system is completely observable. Okay? Alright? Another example. If you form the observability matrix, 1, the first column is 1 minus 2, the other column is minus 1, 2. You can see that the first column is dependent on the second column, they are exactly the same as minus 1. Column, first column, second column. The rank is 1, is less than 2, so the system is not completely observable. Okay, so next, we said that there's a duality theorem relating controllability and observability. Alright? If you want to understand this it's also in Moodle. Remember, I was just saying if you want to understand how controllability matrix is formalized in the second page. Okay? In the second page, if you know what's the transfer function, and because the transfer function is a scalar, GS is the same as GS transpose. You can say that if you have a realization A bar, B bar, C bar, D bar, which is the same as A bar is A transpose, B bar is C transpose, C bar is B transpose, and D bar is D transpose. Then the transfer function's G is the same as GS transpose. Okay? Alright, essentially, what we are telling you here is A, which is a state matrix for your controllable canonical form. You do the transpose. You get the state matrix for your observable canonical form. Okay? Take the C for controllable canonical form, you do the transpose. That is your B. Observable. Take the B of a controllable canonical form to a transpose, and C observable canonical form.
Oh my god.
Okay? So you will go back
So many things to bring.
how you define the controllable canonical form A, B, C, D. So AC is like this. You have the coefficients on the top and the triangular matrix below. Okay? B, C is 1 and 1, 0. CC is B1, all the coefficients for the numerator, and BC is 0. Compare this to the observable canonical form. So if you compare this to observable canonical form, see that AO, which is a state matrix, AO is AC transpose. So instead of the coefficient on top, the coefficient on the side. Okay? BO is CC. CO is BC, and DO is BC. Okay? So the state matrix of the controllable canonical form is the transpose of the state matrix of observable canonical form. Alright? And the B and the C are exchangeable. So if you don't want to memorize so many canonical forms, you just memorize one. You understand that? Just memorize one. If you memorize the controllable canonical form, remember that AO is AC transpose, BO is CC transpose, CO is BC transpose, and DO is BC. Okay, that's observable. Alright? Let's just go through a very quick theory and we'll complete this. So, there's no difference between observable and controllable. It's just a transformation. Okay? We say that the same as controllability, we can also break down a system into observable subspace and an unobservable subspace. Nothing new, right? We can break down a system into observable subspace and a non-observable subspace. Okay? Alright? So, this is useless information. It's just saying that the similarity of transformation matrix, at least I won't repeat. It's just saying that the similarity transformation matrix, you can convert a controllable canonical form to observable. Alright? But the main idea here, okay, what it's trying to say is that if you have an observable part and an unobservable part, the observable part will go into your output. The non-observable part will not go into your output. Okay? Alright? The observable part will go into your output, non-observable part, we're not going to. Alright? So, as another definition of detectability, we actually detect states. So for observable part, you can detect because it goes to output, right? So you can detect your XO, observable states from output. Or you cannot detect your XNO from output. Alright? I would say that it's fine if this unobservable part is stable. Okay, if this is still stable, we say that the plant is still detectable if the unobservable subspace is stable. This is exactly the same as the controllable portion. But controllable portion, we say that controllable parts can be controlled by a different U. The non-controllable part cannot be controlled by the different U. So, alright? So last two slides are the same as the controllable canonical form. We say that we consider a completely observable single input single output system like this, and there exists a similarity transformation that can convert the model to observable canonical form like this. Okay, so see that your AO is AC transpose. Okay, your BO is CC transpose. Your CO is BC transpose. Your BO is BC transpose. So it's always C. Okay? How do you derive this? You can derive this as I said earlier, by saying that GS is GS transpose because GS is the same. Because the derivation is not in the slides, I don't think it's tested. If you're interested, you should know it. Okay, so this is something that is more important. Alright, let's just do a quick summary. When we so just understand that variables are internal variables. Okay? The choice of the state variables is not unique. Okay? So you can have T transformation matrix which is non-singular. And you can either have x1, x2, x3 as states, or x2, x1, x2 as a state, or x3, x2, x1 as a states. So I use the transformation matrix T. And I use the convert. Okay? And this space model can be written as this one. So it's there as BU, one is BU. Closed loop transfer function GS is C plus I minus A plus B plus D. Look at the stability, we look at the eigenvalues of A. Okay, which is also the closed loop location. Alright? Under state feedback, we have C S I minus A minus B K. Okay, memorize the definition of controllability, stabilizability, observability, and detectability. Okay, memorize that. In summary, what is controllability is whether you can control the part. It's you. What is observability? Can you estimate the states? One. Alright? Okay? And very often you can only describe control that you could give can only describe only the completely controllable and observable part of the system. Alright, so in that case, we will only form a partial description. Okay, so that's the end of the lecture for today. Alright, the reason why I'm going slightly faster here is it's all memorization. We are very basic. Okay, so we have more time for revision.
เลย